Hello, future engineers, subscribers, viewers, and students. Here is a video in about solutions to CE licensure exams in hydraulics. And this problem is on water hammer pressure. And I added problems which will enhance your knowledge and skills in water hammer, about water hammer. So I hope that through this video, your skills, your analysis, and your understanding about water hammer pressure will improve. So I usually add questions, problems which will challenge you, and it is about or related to the problem given in the licensure exams. So this is the original problem. A liquid having a density of 800 kilograms per cubic meter flows in a pipe with a mean velocity of 1.275 meters per second. The amount of liquid is known to decrease by 0.13% due to an increase in pressure of 2.5 megapascals. The pipe diameter is 600 millimeters, thickness of 20 mm, and a modulus of elasticity of 140 gigapascals. So which of the following gives, number one, the composite bulk modulus of elasticity of the liquid, the celerity of the pressure wave, the water hammer pressure developed in the pipe for an almost instantaneous valve closure. And this is the additional problem which I mentioned a while ago. And I hope that it will increase your knowledge, especially on water hammer. So for the first part, uh, the celerity of the pressure wave is square root of composite bulk modulus of elasticity divided by the density of the flowing fluid. So E sub C, on the other hand, is equal to the bulk modulus of elasticity of the flowing fluid air divided by 1 plus diameter of pipe, uh, bulk modulus of elasticity of the fluid divided by uh, bulk modulus or modulus of elasticity of the pipe times thickness of the pipe wall. So that is E sub C is E sub B over 1 plus diameter, bulk modulus of elasticity of flowing fluid divided by modulus of elasticity of the pipe material, then thickness of the pipe material. So since everything is known, we substitute E sub B is equal to, we have to solve this first from the formula. E sub B equals negative delta P over delta quantity delta V over V. And delta V is negative because we have here a reduction in the volume, which is 13.13%. So this is negative, so that the bulk modulus of elasticity of the flowing fluid would be positive. So delta P is 2.5 megapascals. I'll change this to 2.5 over 1000 gigapascals. Then delta V over V is 0.13 divided by 100. Negative 0.13 divided by 100. So substituting, so 2.5 over 1000 gigapascals over negative 0.13 over 100. From there, we can solve the bulk modulus of elasticity of the flowing fluid, which is equal to 1.923 gigapascals. So we can now compute the um, composite bulk modulus of elasticity of the liquid substituted to this formula. But before that, let's solve for E sub C. So 1.923 times 10 to the 9 divided by 1 plus diameter 600 mm, bulk modulus of elasticity 1.923 gigapascals, then that of pipe 140 gigapascals, thickness of pipe called 20 mm. So the units here consistent, this is unitless. So the result would be in pascals also, or times 10 to the 9, that's pascals. So E sub C is 1.362 times 10 to the 9 pascals. Substituting to this formula, we can now compute the celerity. 1 square root of 1.362 times 10 to the 9 over density of the flowing fluid, which is 800. So C is 1305 meters per second. Then finally, the water hammer pressure developed in the pipe for an almost instantaneous valve closure. Almost instantaneous valve closure is the same as instantaneous valve closure, and the water hammer pressure develops not only at the valve level but it extends to the reservoir. So the formula for that water hammer pressure is equal to celerity of the pressure wave times density times the change in velocity. And since the valve is closed completely, so the change in velocity is just 1.75. Density is 800, celerity is 1305 meters per second. So the resulting unit would be pascals. So to convert that to kilopascals, we divide further by 1000. So substituting 1305 times 800 times 1.75 divide by 1000. Again, the 1000 is for uh, converting the units from pascals to kilopascals. So pH water hammer pressure is 1827 kilopascals. And for this additional problem, let's have that on the next slide. We proceed to the additional problem. This problem is not a board exam problem, but it will strengthen your knowledge about water hammer pressure. So if the pipe is 800 meters long, determine the water hammer pressure at a point in the pipe 200 meters from the reservoir for a valve closure of A, 1 second, B, 2 seconds, 3, a valve closure where the time of closure is equal to the time for the pressure wave to travel round trip. And this is denoted by capital T, and it is equal to 2L over C. So here is the situation. So this is the normal hydraulic read line, the blue one, when the valve is open and the flow is continuous. Then when the valve is closed, this will be the increase in pressure if the valve closure is sudden or instantaneous. So I will explain it first. When the valve closure is instantaneous, this is the increase in water hammer pressure at the valve. Then it extends up to the theoretically up to the reservoir. So that pH is constant up to the reservoir. So that is the first case where we have instantaneous valve closure. Time of closure is 0, which is impossible in reality. But theoretically, we can do that by just computing what is required in the problem. Then for the case where we have sudden valve closure, this water hammer pressure maximum at the valve will extend for a certain distance before it drops almost linearly. So that's the theoretical assumption to back to normal at the reservoir. The distance of that point where the drop in the water hammer pressure starts to change is denoted by XO from the reservoir. And this XO here is calculated from the fact that the time of closure is T sub C, and it is equal to round trip distance. So 2xo divided by velocity of the pressure wave, which is the celerity in this problem. Then so that's for sudden valve closure. When the closure of the valve is such that the actual time of closure is equal to the time for the pressure wave to travel round trip. So the maximum water hammer pressure only occurs at the valve, then it now drops almost linearly again, or linearly, theoretical assumption, then back to normal at the reservoir. So that's the case where T sub C is equal to T. Then, when the time of closure is less than the time for the pressure wave to travel round trip, this should be the suggested closure in the actual situation in the real world in order not to damage the pipe or in order not to uh, expect unforeseen devastating events. This may burst the pipe, or it may have, who knows, tsunami in the reservoir part. So these are the different situations. So for 4A, the time of closure T sub C is 1 second. Let's compare that to capital T, the time for the pressure wave to travel round trip. So 2xo over, this is the round trip distance, 2xo divided by celerity 1305 equals actual time of closure 1 second. So xo, if it falls in this situation, is 652.5 meters. If it falls in the case where we have sudden closure. Capital T, on the other hand, is 2L over C. So 2 times 800 divided by 1305, and that is 1.226. Since the actual time of closure, 1 second, is less than capital T, so it falls where we have uh, sudden closure, this one. So we can now compute P, P, P1 by similar triangle. So P1 as to x1 is 200 here, is equal to PH as to XO. So T sub C is less than uh, capital T, so it is sudden closure. So again, P1 as to 200 equals PH as to XO, which is 5652.5. So remember that pH is 1827 kilopascals from the preceding slide. So P1 is 560 kilopascals. For 4B, T sub C is 2 seconds. This is now greater than 1.226, so we have slow closure. So the maximum water hammer pressure would now be denoted by pH prime in the figure. And to solve for pH prime, we have to apply similar triangle. So pH prime is lower than pH, so the denominator would be lower time, which is 1.226, and equal to pH as to 2 seconds. So pH prime as to 1.226 equals 1827 pH as to 2 seconds. So pH prime is 1120 kilopascals, and it occurs here. So from the figure again, the increase in pressure at point 1 due to water hammer is denoted by P1 prime. So P1 prime as to 200 equals PH prime as to the length of the pipe, 800. So P1 prime as to 200 equals 1120, PH prime as to 800. So P1 prime is 280 kilopascals. So finally, for C, valve closure where the time of closure is equal to the time for the pressure wave to travel round trip. So this is the situation, and the maximum water hammer pressure occurs only at the valve, and it is pH. So P1 as to 200 equals pH 1827 as to 800. So again, P1 as 200 equals pH 1827 as to 800. So solving for P1 is equal to 456.8 kilopascals. So that's it for this video.